discrete. But we say that one end of it approaches negative infinity and the other end approaches infinity. And we can write down this original signal as the sum of all its harmonics of some sinusoidal function at different with different real coefficients. So let's just call this coefficient ak because we're using the subscript k here. Okay, erase frequently. Because we got the subscript k, let's just call this coefficient ak, and let's use our complex exponential form for our sinusoids. So I know this is going to contain both the sine part and cosine part, but just bear with me for a moment. So we got e to the j omega naught, times k because it's k multiple, and t. And yeah, I believe that's all the work we need to do here. So far so good, right? We are having some assumptions about the function, and I'm just writing out what ideally it's supposed to look like. Actually, now that I think about it, k can also be complex. Reals, not necessarily all real. It could be complex. Anyways, so
yeah, like some coefficient, okay, can be
some coefficient. So now, humanly by expanding out what. Oh yes, another important fact that we need to recognize is that if you were to integrate. Okay, so let me write it out in proper notation first, because I was using the shorthand of just writing the period t here. But if you were to be rigorously keep looking for the eraser. If we rigorously define our integral bounds to be from time t to time t plus capital T, where capital T is the period of your I would say harmonic signal. Yeah, your periodic signal. So t is one given number. Then we can naturally express its integral from starting from any point till exactly where the period is of this function, and which we can expand as. Now I'm just going to use the shorthand, but you understand that nothing has changed here. Yeah, of our ak e to the omega naught kt. Yeah, I forgot the dt here. So we can agree that this is a very special function. Right? I'll just show you why in just a second. Because no, don't pay attention to the JK yet. In fact, using the Euler's identity, we know that this is just some argument for our sinusoids, right? And what you can immediately observe is that for any k that is not 0, this integral is going to give you 0. Do you agree? From taking our humble sine from 0 to 2 pi, of course, our integral is going to be 0. And any multiple of it. Yeah. However, this is not a trivial function, because what if k is equal to 0? What do you get? Is it 1? It's 2. And because we're in signals class, we might as well represent this very special piecewise function as t delta of t. So far, so good. Okay, now this is just a notation thing. We're going to use mostly the piecewise component. Now here's where. Yeah, this is just some compact notation. But next, we're mostly using the piecewise definition, so don't worry too much about this part. So now humor me. With these established relationships, we are going to expand what t of x of t times e to the minus j omega naught L t dt is supposed to be. So we're going to get into why I'm picking this example out in just a second. You'll see. But essentially, what I want to do is, given all the pieces of information that we have deduced, we're going to see what this expands to. So let's just get to it, do some algebra. So we have just we just had the assumption that our signal can be written down as a sum of sinusoids. Okay, fair enough. So we're still going to do our definite integral over a period. We're going to substitute our infinite sum here, k equals to minus infinity all the way to infinity of ak times e to the j omega naught kt dt. Oh, whoops. Terrible blunder. This is only x of t, by the way. Just to write it out. And of course, we have the original component that not changed, minus j lt dt. That looks fine, right? Okay, so that, let's keep going. Let's simplify this to the integral t, having our sigma still, k equals to minus infinity to infinity of, I'm going to take the constant a out because it's inconsequential in the context of the integral. So I'm just going to take it out. It's definitely not zero. So we can first take it out of the, first let's just draw parentheses around this to be more rigorous. And would you agree that because this term in the context of the infinite sum is a constant, therefore we have the associative property where we can put parentheses around this, but also we can treat this entire thing as an argument for the infinite sum. Do you agree? Right? Because here nothing is dependent on k. That's why I'm able to multiply every single one of these arguments with this. And so thus I have expanded the argument of this infinite sum from just this into this entire expression. Fine, right? Okay, I'm going to erase all the unnecessary bits. It's might get distracting later. Oh, okay, this is taking too long. See? No, Neil, what I want you to take away here is the intuition and the process. I see, when I was in like the UFT math circle thing, I used to take pictures of like the notes of our undergrad presenter. But the thing is, it never helped because I kind of zoned out during his presentation because I had no idea what he was saying. Taking a picture after the fact does not really help. So what helps is your understanding along the way, so that you are the one who's able to reproduce all this, well, just from your knowledge, right? So anyway, so that's the big lesson. So let's draw some parentheses around this to help ourselves and to remind ourselves that this whole thing is the argument of the definite integral. Okay, pretty cool. Let's keep going. So now I have told you that because ak is just some constant, both in the context of the infinite sum as well as the definite integral. Do you agree that I can factor this ak out first to here and then to here? All right, let's do that. All right, so over here, we're still going to have exactly what we have here. I'm just going to simplify it. So because these are two exponential functions multiplying each other, we can rewrite this j omega naught k minus l t dt. Looks good. All right, so here you might have some shocking revelations. And also another thing is, because we are performing the integral with respect to, with respect to t, and this summation is only plus k, right? Would you agree if I rewrite this as a k sum from p to infinity? Yeah, no. The reason why I can't double integrate is because we kind of want to keep k like an integer number. It needs to be a discrete quantity. So yeah. So I'm not going to replace it with an integral. So that's instead I'm going to kind of rearrange the order of operation here. I hope that it still kind of makes sense. yeah, I simply reverse the order of operation. Argument remains the same. So now let's focus on this. Does this look familiar? Yeah, it is the same thing. And also, I believe I have left something out over here. I think I did. Yeah, I forgot about that. Yeah, it's just some factor in front. So now let's simplify this guy. We know that this is going to be, so let's rewrite this. AK, yeah, I'm going to use the shorthand notation again. K infinity of u t delta a minus L. And we know that this expression is going to be evaluated to AKT when K equals to L, right? And yeah, you can give this a name. You can call it AL if you want. So now we're at the crux of this. So now that yeah, this is K here, not T. Oh yeah, I can see the. This is thanks to Discord compression and Apple's webcam. Oh, geez. Oh, okay, okay. Yeah, yeah. So this is K. Right. Yeah. Okay. Wait. Actually, is this? Did you see all my symbols flipped on your side? It looks mirrored on. Okay. Okay. So yeah. So the K never changed here. My point here is that this expression is only meaningful when our two like kind of arbitrary harmonic coefficients happen to be the same, which is big because now we have an expression of AK with respect to an integral that we can evaluate given any defined function. So therefore, we can say that AK is equal to 1 over t of the periodic integral of your x of t e to the minus j omega naught k t dt. And yeah, that's the end of my presentation. So remember how the first question on the assignment is to break up a discrete time signal into like a sum of harmonics, right? This is how you get its constants, the coefficients. And of course, this is given. Yeah, exactly, right? That's why I said, doesn't this look familiar? And of course, another piece of information here is that we've been using omega naught all along. And of course, that's some sort of predetermined fundamental frequency. I still don't know. Here's what I think, Neil. I think you could pick any fundamental frequency at the beginning and you'll just get different series that all ultimately converges to the same thing. Do you agree? Yeah, my point here is that it will change your individual terms, but it does not change what it converges to. Okay. Oh, dude. Yeah. After giving you this little mini lecture here, it also kind of makes sense for me. The reason why we want only uh, harmonics of our this fundamental frequency is actually really arbitrary, like we discussed. So we can pick any arbitrary frequency, and we can write out a series based on it consisting only of terms that are integer multiples of that original frequency, aka harmonics. So it only works when this is true. But what I thought before was actually what I thought before is kind of true as well. If you just have period of frequency of 1 and then 2 and then 3, well, in that case, my fundamental frequency is 1. So that also works out, but I didn't know what the underlying assumptions and the restrictions were. So I think now things are a lot more clear. Yeah, Fourier spectra are simply where your AKs are. So here you have I think multiples, and you just basically performing Fourier transform, but not